In this video, we are beginning section 1.1 on numbers and sets. So our goals are to define different types of real numbers. We're going to express inequalities on number lines and construct the intersection and union of sets. So in this video, we are going to focus on reviewing the types of real numbers. So let's get right into a definition and some review. Okay, so when we talk about the numbers 0, 1, 2, 3, 4, 5, and so on, all of those whole numbers, we call these the naturals. So the natural numbers, or the naturals, and the symbol for the naturals is a capital N with an extra vertical line next to that first one. So that's the symbol for naturals. So if we include the negative versions of those, like -1, -2, -3, and so on, we call those the integers. So those are the integers now. And the symbol for integers is a capital Z. A capital Z with an extra line along this diagonal one. Okay, the next type of number we're going to review is the rationals. So the rationals, and the symbol for rationals is a capital Q with an extra vertical line kind of down the left here. The rationals are numbers that can be written as a ratio. And a ratio is just another word for fraction. So they can be written as a ratio or a fraction of two integers. So we have a fraction of two integers, a over b, where the a and the b are integers, and that denominator b is not allowed to be 0, right? Because we can't divide by 0. That makes a fraction undefined. Okay, so here are some examples. If I have something like -4 divided by 9, both of those numbers are integers. The bottom is not 0. So that makes that whole fraction rational. What about if I have a decimal number like 0.4? Is that rational? So well, with 0.4, let me switch colors. I can write that as a fraction because that's 4 over 10. And I could further simplify that. I could divide the top and the bottom by 2 to get 2 over 5. So that is a fraction of integers, or a ratio of integers. So that is also rational. Okay, what about if I have a decimal like this that repeats, 0.3333 repeated? Or I can write that repetition with this bar over the 3. Well, you might remember from algebra like how to write this as a fraction. Well, this is the fraction 1 over 3. So because it can be written as a fraction of integers, that is a rational number. Okay, awesome. All right, well, we have rationals. And then on the flip side, we have what are called irrationals. So irrationals are real numbers that are not rational, meaning they cannot be written as a ratio of integers. Okay, so let's give some examples of these. Okay, so, a common example is something like square root of 2. Square root of 2 is irrational. In fact, if I have any type of root that is not nicely simplified to like a whole number, and that includes cube roots or fourth roots, it's going to be irrational, it turns out. So if I have something like the cube root of 7, that does not simplify to a nice whole number. And I can even do something a little bit more complicated with it. I could divide the whole thing by 4. I could stick a negative sign in front of it. It's still going to be irrational, it turns out. Okay, and there's maybe 2 very common examples that you might remember from having seen them before. So give the video a quick pause for about 30 seconds. Can you come up with 2 other examples? None of them involves square roots, although there are others that involve square roots. Can you think of a couple examples that don't involve roots? Pause the video in 4, 3, 2, 1. See if you can come up with a couple examples. All right, so hopefully you did that. Hopefully you gave the video a quick pause to think about some examples. All right, so one example is pi. So pi is approximately, here's my approximately equal symbol, is approximately 3.14, although the decimals do go on forever. Okay, another example of an irrational number is e. And e as a decimal is about 2.7. We're going to review e much later in the course, in the second half of the course. Okay, so those are examples of some irrationals. And if you put the rationals and the irrationals together, we get the reals. And the symbol for the reals is a capital R with an extra vertical line next to that first one. I never wrote the symbol for irrationals. And it turns out there is actually no symbol for the irrationals. So the others all have symbols. The irrationals, unfortunately, don't have a symbol. Okay, so the reals are numbers that can be represented on a number line. Okay, so they're basically all the rationals, all the irrationals put together. So if I have a rectangle, here that denotes all of the reals, any real number, and my symbol for reals is, a double vertical line, and then I draw that capital R. Within that reals rectangle, imagine I have a circle that contains all of the rationals. So the symbol for rationals is that capital Q with that extra vertical line there. Well, then what would be all of this stuff? All of the stuff that's not in the rationals circle, but still nonetheless inside of that reals rectangle. Well, that's all the irrationals. All the irrationals are reals that are not rational. Okay, that's just sort of a visual way to think about those three. Okay, all right, so let's talk about some of these things in decimal form. So in decimal form, let's talk about rationals and irrationals. It turns out rationals in decimal form can do one of two things. Either they terminate, and let me give an example of this. So something like 2 over 5, that fraction is 0.4, right? We saw that up above here. 0.4 is the same thing as 2 over 5. So this decimal number stops. The decimals don't keep going past the 4. In other words, they terminate. Terminate just means they stop. The decimal stops somewhere. Okay, but there's another possibility. Rationals could also do something like we saw with 1 over 3. 1 over 3 in decimal form just was 0.3333 repeating forever. So they could go on forever, but if they do go on forever, it turns out they do need to repeat in order for us to be able to express it as a nice fraction of integers like this. Okay, so in decimal form, rationals will do one of these two things. Irrationals, on the other hand, go on forever. They go on forever, but they don't repeat. They are never going to repeat like that. Okay, and an example is pi. Pi in decimal form, I'm going to write a bunch of digits, is about 3.1415926535 ... It keeps on going on forever, and it actually never repeats. Of course, you don't need to know all of those decimal digits. I just care that you know the 3.14. I just care that you know that much of it. Okay. All right. So you might also remember stuff from before, like called imaginary numbers or complex numbers. In our class, we are not going to use either of those. If we do get something that would be imaginary or complex, so those are things like with I, when you get like square roots of negative numbers, we're going to say things like that are undefined, or we can say that they do not exist. Okay, so in our class, we're not going to be using imaginary or complex numbers at all. All right, let's look at some examples. So let's evaluate the expressions. So part A says, what if I want to do 1 divided by 0? What's something divided by 0? Well, let's see if we can motivate the answer for this. If I wanted to do something like 21 over 3, how would I do that? Like, intuitively I know the answer is 7, but why? Why is 21 divided by 3 7? Like, what does that mean when it's asking us to do that division? What it means is we want to figure out a number that when you multiply by 3, it equals 21. In other words, 3 goes into 21 sort of how many times? So what is that number you'd multiply 3 by to get 21? Well, it's 7. And that's why 21 divided by 3 is 7. Okay, so using that same logic, what would happen if I did 1 divided by 0? What would that mean? Well, it would mean 0 times what equals 1. So 0 times what equals 1? Well, with this, nothing works. Nothing works, since if you do 0 times anything, well, 0 times anything is 0. Okay, so I'm going to put a sad face. But we needed it to equal 1, but it's impossible for it to equal 1. Okay, so as a result, because nothing works, we say that 1 divided by 0 is undefined. It is undefined. Okay. All right, so I'm going to go ahead and write that here. 1 over 0, my answer to that is undefined. Okay, and I'm going to introduce one math symbol, which is, I'm going to put a sort of an arrow like this. And the arrow, when I write the arrow like that, it just means this implies. So the previous line, where we had that reasoning, well, that implies that our answer is undefined. Okay. So when I divide by 0 like that, it's undefined. I'm going to leave it for you to think about, well, if I did 0 divided by 0, well, what is that going to be? It turns out it's also undefined, but there's a slightly different reason for why. That would be a good exercise to practice. Okay, let's do part B right here. What if I have square root of -4? So when I find a square root of a number, I'm trying to find a number x, so that when I square x, it equals -4. Well, we're not using any imaginary numbers in our class. So with this equation, well, there's nothing that's going to work. There's no real solution. I'm going to abbreviate solution, S-O-L-N, since, well, when you square something, that's always going to be greater than or equal to 0. So there's no way it's going to equal -4. Okay, so because I can't find an answer for this or find a value, square root of -4, well, that's also undefined. In fact, you might remember that I'm going to switch colors, any even root of a negative number is undefined. So this was a square root, but if I did a 4th root or a 6th root of a negative number, it's going to be undefined for the same type of reason. Okay, and what I want to end this video with is just by drawing a distinction between two phrases that are often confused for one another. So we say the phrase no solution for an equation, so that's something that has an equal sign, that has no real answer, like x squared equals -4. So if I have an equation, something with an equal sign, I'm trying to solve, and there's no real answer, well, we say there's no solution. On the other side, on the other hand, we say something like undefined or does not exist, which I can abbreviate as DNE. We say those for expressions. Expressions are, mathematical things that do not have equal signs. So an example of that would be something like 1 divided by 0, this previous problem. For that, we would say undefined. Okay, for an expression like that, that isn't a real value. That is undefined.